So we're going to talk now about the idea of dimension. This is an idea that I think most students have some intuition for, some geometric intuition. You have some sense for what it means for something to be two-dimensional or three-dimensional. Turns out that dimension is a concept that is extremely useful for lots of computations. And in order to be used for computations, we need to be able to prove theorems about dimension. And of course, in order to prove theorems about it, we need to have a definition. So we find ourselves in need of a definition of dimension, even though, of course, we already have some geometric intuition for it. The sticky point is that we are not simply in need of a definition of dimension for spaces of vectors that we're already familiar with, things like R2 and R3. It'd be pretty satisfying to make an easy definition for the dimension of R2. We'll just say that's two-dimensional. But we have now different kinds of vector spaces, abstract vector spaces. We need to be able to define dimension for those things as well. We have no existing intuition for what dimension should be for one of these abstract vector spaces. So we find ourselves in fact, a fairly difficult situation of needing to make a definition for something that we don't have any intuition for. So building up to this definition is going to take several pages of discussion. We're going to start off with an introductory theorem here. And this theorem says that if you have a basis for a vector space. Now again, this is any vector space. This is not necessarily Euclidean. If you have a basis for a vector space, and if you furthermore have a collection of vectors in that vector space, the number of which is greater than the number of vectors in your basis, then that list of vectors must be linearly dependent. That's an interesting little theorem. So I like to think of this, phrase this in a slightly different way, and say that any list of vectors that is more numerous than a basis must be dependent. It's a nice way to think about it. More numerous than a basis. Okay. All right. So we're going to spend the next couple of pages proving this initial theorem, and the definition of dimension turns out will relate to this. Okay. So we're going to start off by observing that because this is a basis, each one of these W vectors can be written as a linear combination of these basis vectors. You'll notice here I have a linear combination in each one of these equations I have written down here. I'm writing one of the W vectors as a linear combination of these basis vectors. And then furthermore, we know that this can be done for each one of these W vectors. This can be done in a unique way. All right, now, natural question to ask at this point: why did I write these equations in this awkward vertical way? I didn't have to do this. It turns out that this is going to end up being kind of convenient in the calculation on the next page. So for the moment, let's just put a pin in that. Okay. All right. So having done this, we're going to take these coefficients exactly as they are on the page here. We're going to lift them straight off of the page and make a matrix out of them, like so. That doesn't quite fit. So we're going to take all of these numbers, lift them straight off the page, and make a matrix. All right. Now there's a temptation to look at this and think system of equations. It's important to realize this is not a system of equations. This thing here, not a system of equations a la Chapter 1. Here we do not have a bunch of constants, numbers that are linear combinations of variables x1 through xn. These are all, in fact, vectors. right? V1 is a vector, V2 is a vector, etc. So this is not a chapter 1 style system of equations, so the fact that we've written it awkward, in a significantly different way, not really inconsistent with anything. Okay. All right. So take those coefficients, make a matrix, and call that matrix A. We'll come back to that. All right, so what do we do with this setup? Well, we're going to state and prove what's called a lemma. This is something that we need to use for a proof that we're in the process of, but that's sort of a side calculation as part of that proof. So the term is lemma. And here's the lemma. The lemma says that if you have a linear combination of these W vectors, then that linear combination is a linear combination of the V vectors, but furthermore, that these C coefficients, thought of as a vector, relate to these D coefficients, thought of as a vector, by way of this matrix A. That's the same matrix A that we have back here. Okay. All right, so proving this is really just a kind of a plug and chug calculation. You'll notice that what we have here is a linear combination of linear combinations. You can see it right here. It's a linear combination of what we've already established are linear combinations of the V vectors. So really all we're going to do is we're going to take this expression here, we're going to multiply it out in collect terms. And we're going to find that when you multiply it all out in collect terms, that the coefficients end up being these numbers. Specifically those numbers that are computed by this formula. So here we go. Let's see here, I'll use yellow. So here we have this linear combination of these W vectors. I haven't really done anything here. All I'm doing is just expanding out what those vectors are. Remember that each W vector is a linear combination of the V vectors, and there's that familiar vertical writing of these formulas. That's these formulas that we saw on the previous page. Okay, so writing those out vertically, we have this. Okay, well, so let's multiply that all out and collect terms together, and that gives us this. And you can see where these numbers come from. Where do these V1 coefficients come from? These are all coefficients of V1. Well, here's the V1s, right? And those coefficients all added together. Well, you have C1A11, and then C2A12, and then CMA1M. So that's just really very directly and literally collecting all these V1 terms and putting them all together. Okay. Likewise for the V2 terms, we have C1A21 V2, and we have C2A22 V2. So here again, I'm collecting all of these V2s together, etc. All right, and notice that what we have is, as expected, or as required, we have a linear combination of the V vectors. Here it is. We have a linear combination of our V vectors. So these numbers must be these D's. Of course, there's always a unique way to write any vector as a linear combination of basis vectors, and these V vectors are basis vectors. So there's our explicit formula for how to compute these D numbers from these C numbers. It's this explicit formula, and you can collect all those together. D1 is computed by that, and D2 is computed by that, etc. So we get this little system of equations, and now we just have to make the observation that this is a familiar construction. That is exactly the matrix A. There's our coefficients of our matrix A. This is exactly the matrix A from the previous page, times this vector C of coefficients C1 through Cm. It's exactly a matrix vector multiplication. Okay. And so now you can see why it was that we wrote these equations sideways like this. We had to write these sideways so that these numbers would be arranged in the way that would be consistent with what they had to be, because this is how matrix multiplication works. Right? And if I had written these equations the other way, if I'd written these equations in the way that looked more sort of familiar, things would have been backwards. And by the way, you can look in the book and see how the book does this. The book writes these exact same equations and then says, oh, hey, by the way, when we make this A matrix, we're going to take these coefficients and, well, just sort of flip them before they make a matrix. So it was a little uncomfortable and awkward. Okay. All right, so this is just details. Again, I emphasize all we've done here is take this expression, plug in how these W's are linear combinations of V's, and multiply it out. Okay. All right, so our lemma is proved. So, with that done, let's go back to the main proof. Okay. M is bigger than N. That means that our matrix A has more columns than rows. Let's go back to where we defined it. M is bigger than N. Therefore, there are more columns than rows. Said differently, there are more W vectors than there are V vectors because of this. Right? This list of W vectors is more numerous than this basis. All right, so this is what you might loosely call a short and wide matrix. It has more columns than rows. Okay. Well, since it has more columns than rows, that means that this has a non-trivial solution. Right? Just think about pivots. There's only so many pivots, at most one pivot per row. But there are more columns than that, therefore there are free variables, and therefore there are non-trivial homogeneous solutions. So that's all old Chapter 1 argument. Okay. All right, but now let's take another look at this equation here. AC equals 0, what does that tell us? AC equals 0 tells us that that C linear combination of the W vectors gives us the 0 linear combination of the V vectors. That's what we have right here. Right? These are the coefficients in a linear combination of the W vectors. These are the coefficients in a linear combination of the V vectors that gives you the same vector. In other words, when you multiply it out and collect terms, that's what you get. And of course, this trivial linear combination of the V vectors is the 0 vector. So altogether then what we have is that we have a non-trivial, significant, in other words, linear combination of the W vectors that equals 0. And that means that this list of vectors is linearly dependent as required. Okay, it's a long way to go for a result, but it turns out that this is going to be exactly what we need to make our definition of dimension